coastal England, late 1940. The nocturnal raids, once sporadic, had become a relentless drumbeat against the industrial heartlands and port cities. Luftwaffe bombers, initially detected at predictable ranges by the chain-home radar stations, now seemed to materialize closer, their formations tighter, their bombing runs more accurate than the nascent British air defenses could effectively counter. This sudden, unsettling improvement in German navigation and bomb aim suggested a profound shift in their electronic capabilities, a technological leap that threatened to unravel Britain's already strained defensive network and potentially cripple its war effort. Dr. R.V. Jones, Assistant Director of Intelligence, Science at the Air Ministry, received the first detailed reports of these anomalies. His initial assessment, based on intercept logs from Y stations, pointed to the use of a new German radio navigation system, christened Nicobine by British intelligence. The system appeared to employ highly directional radio beams, guiding bombers with an accuracy previously unattainable, allowing them to penetrate deeper into British airspace under cover of darkness and deliver their payloads with devastating precision. The German system, as pieced together from captured equipment and radio intercepts, operated on very high frequencies, specifically in the 30 to 33 MHz range. This was a significant departure from earlier, lower-frequency navigation aids, and it allowed for narrower, more focused beams. British technical analysis, conducted at the Telecommunications Research Establishment, TRE, indicated that the Nicobine transmitters projected two overlapping beams, each modulated with a distinct audio tone. A bomber pilot, flying along the precise intersection of these beams, would hear a continuous, undifferentiated hum, indicating he was on course. Deviations to either side would produce a Morse code dot or dash, guiding him back to the central path. Further examination of the intercepted signals revealed the remarkable stability and power of these beams. The German engineers had evidently achieved a level of control over their high-frequency transmissions that British radar experts, still grappling with the limitations of their own vacuum tube technology, found difficult to replicate. The sheer range at which these precise beams could be maintained, extending hundreds of miles from their continental European origins, underscored the sophistication of the German development. Production logs from Telefunken, later recovered, confirmed a steady increase in the deployment of these specialized high-frequency transmitters throughout 1940. The implications were stark. If the Germans could project such precise, high-frequency radio energy across the channel, guiding their bombers with unerring accuracy, then the fundamental assumptions underpinning British air defense were in jeopardy. The chain-home system, while effective for early warning, lacked the precision for effective night fighter interception against such a guided threat. The strategic balance of the air war, a precarious equilibrium, seemed to tilt decisively in Germany's favor with each passing night. The British radar engineers at Bawdsey Manor and later at Telecommunications Research Establishment, TRE, in Malvern, had by 1940 achieved remarkable progress in their own radar systems, primarily operating in the VHF band, typically between 20 and 200 MHz. Their chain-home and chain-home-low (CHL) networks provided early warning against incoming aircraft, a critical defense during the Battle of Britain. These systems, however, were bulky, required large antenna arrays, and suffered from limited resolution, making them unsuitable for precise targeting or airborne interception. Their understanding of German radar technology, gleaned from intelligence reports and captured equipment, suggested a similar reliance on longer wavelengths. Freya, the primary German early warning radar, operated around 125 MHz, while the Würzburg ground-controlled interception radar used frequencies near 560 MHz. Both were impressive engineering feats, demonstrating robust construction and effective range for their respective roles. The Würzburg, in particular, with its parabolic dish, represented a significant step forward in aiming precision compared to British CHL. However, a growing body of evidence began to confound these assumptions. Allied bomber crews reported instances of unexpectedly accurate German anti-aircraft fire, even in conditions of poor visibility, far exceeding what was thought possible with existing Wurzburg systems. Fighter pilots described encounters where German night fighters seemed to acquire them with unnerving speed and precision, again suggesting a capability beyond known German airborne radar. These anecdotal accounts, while often dismissed as pilot exaggeration or combat stress, accumulated into a pattern too consistent to ignore. In 1942, the first tangible pieces of this puzzle began to arrive. Fragments of German airborne radar equipment, salvaged from downed aircraft, reached British laboratories. These components, particularly their waveguides and resonant cavities, hinted at operating frequencies far higher than anything the British believed the Germans possessed. The internal construction of these German devices, while robust, did not immediately reveal the full extent of their capabilities. But the precision machining and material choices pointed to advanced manufacturing. One particular component, a small, intricate cavity magnetron, was recovered from a shot-down Ju-88. Its internal structure, a series of resonant cavities arranged around a central cathode, was superficially similar to early experimental British designs, but its dimensions were dramatically smaller, implying operation at much shorter wavelengths. Initial tests, conducted with great care due to the component's rarity, indicated frequencies in the centimetric range, specifically around 10 centimeters or 3 gigahertz. This was a frequency band the British themselves were only just beginning to exploit with their own highly secret cavity magnetron. The implications were profound. A 10-centimeter radar offered vastly superior resolution and could be fitted into much smaller airborne platforms, revolutionizing airborne interception and ground-controlled anti-aircraft fire. The British had developed their own cavity magnetron in 1940, a breakthrough that had been shared with the Americans in the Tizard mission, forming the cornerstone of Allied centimetric radar development. The idea that the Germans had independently achieved a similar, if not identical, technological leap and had deployed it operationally was almost inconceivable. The initial reaction among some senior British radar scientists was outright disbelief. The technical challenges of producing a high-power, reliable magnetron at centimetric wavelengths were immense, requiring specialized materials, vacuum technology, and precision engineering that they believed only the Allied nations, with their concerted research efforts, could master. "This is impossible," one senior engineer reportedly stated. Upon examining the recovered German magnetron, the prevailing view was that the Germans lacked the fundamental understanding of microwave physics necessary for such a device. Further analysis of the German magnetron revealed a design that, while effective, appeared less refined than the British equivalent. Its construction suggested a more empirical development path, perhaps indicating that the Germans had stumbled upon the design rather than derived it from first principles. However, its operational presence was undeniable. The existence of this German centimetric device forced a re-evaluation of all assumptions about the enemy's technical capabilities and the security of Allied technological advantages. The discovery shifted the strategic landscape dramatically. If the Germans possessed centimetric radar, then Allied countermeasures, such as chaff, which was designed to disrupt longer wavelength radars, would be far less effective. Furthermore, the vulnerability of Allied bombers, especially at night, would increase significantly. The race to develop more effective jamming techniques and even more advanced radar systems became even more urgent. Occupied France, August 1943. The German radar engineers, confident in their technological superiority, found their world beginning to fracture. Reports from the Eastern Front, initially dismissed as anecdotal, spoke of Soviet aircraft equipped with radar systems operating at frequencies previously deemed impossible for airborne deployment. These were not the bulky, low-frequency arrays familiar to the Luftwaffe, but something far more compact, more potent. The implications were immediate and severe. If true, the strategic advantage held by German radar, particularly in night fighting and anti-shipping operations, was eroding with alarming speed. The integrity of their air defense network, built on the assumption of superior detection capabilities, was suddenly vulnerable. The opportunity for a direct examination arrived in late February 1943, following the capture of a British Sterling bomber downed near Rotterdam. Luftwaffe recovery teams, accustomed to salvaging wreckage for intelligence, approached this particular crash site with heightened urgency. The bomber, a 4-engine heavy, had fallen largely intact into soft ground, preserving much of its internal equipment. Among the twisted metal and shattered instruments, a peculiar device was located near the forward fuselage, distinct from the standard communications gear. Its unusual shape and robust construction immediately drew the attention of the ordnance specialists. This device, roughly cylindrical and approximately 10 centimeters in length with a diameter of 5 centimeters, was unlike any German component. It was heavy for its size, suggesting dense internal construction, and featured a series of cooling fins around its exterior, indicative of significant heat generation during operation. The primary material appeared to be copper, meticulously machined and brazed. Electrical connections were robust, designed for high power input. Initial field assessments, conducted by junior technicians under armed guard, noted its resemblance to experimental high-frequency oscillators, but the power output implied by its construction seemed beyond conventional German vacuum tube technology for such a compact form factor. Transported under heavy escort to the Telefunken research laboratories in Berlin, the component underwent a more thorough inspection. Dr. Rudolf Hilsch, a leading expert in high-frequency physics, directed the examination. His team meticulously disassembled the device, revealing an intricate internal structure, a central cathode surrounded by multiple resonant cavities, machined with extraordinary precision. These cavities, 8 in number, were connected by slots to a central interaction space. The anode block itself was a single piece of copper, suggesting a sophisticated manufacturing process. The presence of a strong permanent magnet integrated into the housing was a critical observation, confirming its function as a magnetron. Quantitative analysis of the cavity dimensions and the magnetic field strength allowed for a theoretical calculation of its operating frequency. The results were astounding. The device was designed to generate microwaves in the 10-centimeter wavelength band, corresponding to a frequency of approximately 3 gigahertz. German radar systems, by contrast, operated primarily in the meter and decimeter bands, with their most advanced airborne systems struggling to achieve wavelengths below 50 centimeters. This 10-centimeter magnetron represented a leap of an order of magnitude in frequency, directly translating to vastly improved angular resolution and reduced antenna size for a given performance. Further tests, conducted with specialized high-voltage power supplies, confirmed the magnetron's output capabilities. It produced pulsed power exceeding 10 kilowatts, a figure that dwarfed the output of comparable German klystrons or triodes operating at even lower frequencies. The efficiency of the device, converting electrical energy into microwave radiation, was also remarkably high, above 50%, minimizing heat waste for its compact size. This combination of high frequency, high power, and compact form factor was the key to its strategic value, enabling smaller, more precise radar sets for aircraft and ships. The implications for German radar development were profound. The British had not merely caught up, they had surpassed German capabilities in a critical domain. The existence of such a device meant that Allied aircraft could carry radar systems with significantly smaller antennas, less susceptible to detection, and capable of far greater precision in targeting. This technological chasm, suddenly revealed, demanded an immediate and comprehensive reevaluation of every aspect of German air defense and offensive strategy. The engineers, holding the alien device in their hands, confronted a future far more complex than they had imagined. Occupied France, August 1943. A crumpled German radar set, a Freya FUMG-40, lay partially obscured by debris. Its antenna array twisted into a grotesque sculpture against the shattered remains of a farmhouse. British intelligence, through a network of courageous resistance operatives, had pinpointed its location weeks prior, the target designated for a daring commando raid. The stakes were immense. Allied bombers were suffering unacceptable losses over the Reich, and the Germans' increasingly sophisticated air defense network, centered on these radar installations, was proving devastatingly effective. Understanding the enemy's radar technology was paramount to developing countermeasures that could save thousands of aircrew lives and turn the tide of the air war. The commando team, having secured the site under intense enemy fire, worked with practiced efficiency to dismantle the crucial components. Their primary objective was the core of the radar, the transmitting and receiving units, which they carefully crated for immediate transport back to England. The journey was fraught with peril, a clandestine relay across occupied territory, through U-boat-infested waters, and finally to the secure laboratories of the Telecommunications Research Establishment, TRE, at Malvern. There, a team of Britain's brightest radar engineers, led by figures like Dr. R.V. Jones, awaited the prize with a mixture of anticipation and dread. They knew the Germans were good, but the scale of Allied losses suggested something more than just incremental improvements. Upon arrival, the crates were unsealed in a sterile laboratory environment, the components laid out on long, wooden benches under the harsh glare of inspection lamps. The engineers, a cadre of brilliant minds who had pioneered much of the world's radar technology, began their meticulous examination. They probed circuits, tested materials, and analyzed the intricate wiring. The Freya, a long-range early warning radar, operated at a relatively low frequency, around 125 MHz, and its general architecture was familiar. It confirmed their existing intelligence regarding German capabilities in this band. The initial assessment was that the Germans had indeed built a robust and reliable system, but nothing revolutionary. Then came the examination of the Würzburg-Reese, a much more advanced German fire control radar, also captured in a separate operation. This system, operating at a higher frequency of 560 MHz, was notorious for its precision, guiding anti-aircraft artillery with deadly accuracy. The engineers disassembled its transmitter unit with surgical precision. They expected to find a powerful triode or tetrode valve, perhaps a new design, pushing the boundaries of conventional vacuum tube technology. What they found instead, nestled deep within the Würzburg's heart, was a cylindrical copper block, approximately 10 centimeters in diameter, with multiple resonant cavities machined into its interior. This was not a valve they recognized from German schematics. Dr. John Randall, one of the original inventors of the cavity magnetron, was among the first to lay eyes on the component. His hands, usually steady, trembled slightly as he picked it up. The internal structure, the arrangement of the cavities, the central cathode, it was unmistakably a cavity magnetron. Not just any magnetron, but one strikingly similar in design to the British-developed 10-centimeter magnetron, a device that had revolutionized Allied radar. Production logs later confirmed the German unit was capable of generating peak powers of 5 to 7 kilowatts, a formidable output for a device operating at such high frequencies. This was the very technology that allowed Allied aircraft to carry compact, powerful airborne radars, enabling night bombing and anti-submarine warfare with unprecedented effectiveness. A stunned silence fell over the laboratory. The implications were immediate and profound. The Germans possessed the cavet. Why magnetron? A technology they had believed to be a closely guarded Allied secret, one of their most significant technological advantages. Further analysis of the German magnetron designated the Magneteinschub, magnetic insert, in their documentation, revealed that while it was a magnetron, it was not an exact copy of the British design. It had been independently developed, likely stemming from earlier research into multi-cavity magnetrons that had been abandoned by the British in favor of the more robust Randall and Boot design. German production records indicated initial operational deployment in late 1942, coinciding with the sharp increase in Allied bomber losses. The realization was a bitter pill. The enemy had independently arrived at a critical technological breakthrough, one that the Allies had believed gave them a decisive edge. Interrogation files later revealed that German scientists, particularly those at Siemens and Telefunken, had been working on magnetron designs since the late 1930s, exploring various configurations. Their path to the cavity magnetron, while parallel, had been slower, hampered by a lack of focus and material shortages. The captured German magnetron was a testament to their engineering prowess, even if it confirmed a strategic parity that had been entirely unexpected. The war in the air, already a brutal struggle, would now be fought on a more level technological playing field than previously imagined. The implications of the magnetron's capture began to crystallize within the German high command. Intelligence summaries, compiled from interrogation transcripts and technical analyses, painted a stark picture of Allied radar capabilities. The initial shock, a mixture of disbelief and professional affront, slowly gave way to a cold assessment of strategic vulnerability. The Luftwaffe radar development teams, particularly those at Telefunken and Siemens, had dismissed the cavity magnetron as an impractical laboratory curiosity, too complex and unstable for field deployment. Their own efforts focused on klystron and triode-based systems, which, while robust, operated at significantly lower frequencies and power outputs. The captured British H-2S radar, with its 10-centimeter wavelength, represented a leap in resolution and stealth that their current technology could not match. A technical report dated October 1943, originating from the Reichsluftfahrtministerium, detailed the performance metrics of the captured magnetron. It generated peak power outputs of 25 kilowatts, a figure that dwarfed the typical 1 to 2 kilowatts achieved by German airborne intercept radars. This immense power, coupled with its high-frequency operation, allowed for the detection of smaller targets at greater ranges and with unprecedented angular precision. The strategic ramifications were profound. Allied bombers, previously detectable at long ranges by German Freya and Würzburg systems, could now be guided with an accuracy that threatened the entire German air defense network. The ability of the H-2S to map terrain from altitude, even through cloud cover, meant that precision bombing raids could continue regardless of weather conditions, negating a key advantage previously held by the Luftwaffe. This internal navigation capability also suggested a reduced reliance on vulnerable ground-based navigation beacons. Production logs from British factories, later acquired through espionage, indicated a steady output of these magnetrons, numbering in the hundreds per month by late 1942. This suggested not a prototype, but a fully operational and widely deployed system. The scale of Allied commitment to this advanced radar technology was undeniable, transforming it from an isolated incident into a systemic threat. The German scientific community, initially skeptical, now faced the undeniable truth of a technological gap. The Kriegsmarine also noted the implications for anti-submarine warfare, realizing that similar high-frequency radars could dramatically improve the detection of U-boats on the surface. The entire spectrum of German military operations, from air defense to naval patrols, suddenly appeared exposed to an unseen and highly effective enemy. A directive from Field Marshal Erhard Milch in November 1943, addressed to all Luftwaffe research and development centers, underscored the urgency. It called for an immediate and comprehensive reevaluation of all radar programs, with a specific mandate to reverse engineer the magnetron and develop countermeasures. The race was on to close a technological chasm that had opened without their prior knowledge. The capture of the magnetron had not merely revealed a new Allied weapon. It had exposed a fundamental miscalculation in German technological intelligence and strategic foresight. The enemy possessed a capability that had been deemed impossible, and the consequences would reshape the aerial war. Berlin, March 1943. The first detailed technical reports concerning the Allied cavity magnetron began to circulate among the Reich's top radar engineers. These documents, derived from captured equipment and intelligence intercepts, described a device capable of generating microwave frequencies at power levels previously deemed impossible for compact airborne units. The implications were immediate and profound. Allied aircraft, particularly bombers, could be equipped with radar systems offering vastly superior resolution and resistance to German jamming efforts. The initial reaction within Telefunken and Siemens, the leading German radar manufacturers, was a mixture of bewilderment and outright skepticism. Dr. Rudolf Kuhnhold, a pioneering figure in German radar development, found the reported specifications difficult to reconcile with known physics and engineering capabilities. His team had been working for years on centimeter-wave radar, achieving modest success with klystrons and traveling wave tubes, but nothing approaching the power outputs now attributed to the Allied magnetron. Production logs from British factories indicated a manufacturing rate of hundreds of these devices per month, suggesting not a prototype, but a mature industrial-scale deployment. This scale of production, coupled with the advanced performance claims, fueled the disbelief. German engineers understood the immense challenges of fabricating such a complex vacuum tube with the necessary precision and material purity. The idea that an adversary had not only solved these problems, but was mass-producing the solution, felt almost like a fabrication. Interrogation files from captured Allied airmen, corroborated by technical analysis of downed aircraft components, consistently pointed to the widespread use of these microwave radar sets. The sheer volume of evidence began to erode the initial resistance, yet a core of skepticism persisted. Some theorized that the Allied intelligence was deliberately exaggerating capabilities to sow fear and divert German research efforts. The strategic implications were stark. If the Allies truly possessed such radar, their night bombing campaigns would become far more accurate, and their air defenses, particularly against U-boats, would be significantly enhanced. This would necessitate a complete reevaluation of German air and naval strategy, demanding countermeasures that did not yet exist. The quiet reflection among the German engineers was that their own radar development had fallen dangerously behind. Interrogation files from captured Luftwaffe ground personnel in late October 1943 began to corroborate the initial findings. These reports detailed new Allied jamming techniques observed over the Ruhr, characterized by a sudden, overwhelming noise floor that rendered their Würzburg and Freya sets nearly useless during critical phases of bomber streams. The descriptions consistently pointed to a broad-spectrum interference, unlike the more localized, narrower band jamming previously encountered, suggesting a fundamental shift in Allied electronic warfare capabilities. Production logs from Telefunken and Siemens, analyzed from captured documents in November, revealed a frantic acceleration in German countermeasure development, specifically targeting the 10-centimeter band. This sudden focus on an entirely new frequency range, previously considered secure due to the perceived technical impossibility of generating high-power microwaves, underscored the German High Command's growing alarm. Engineers at these facilities were reportedly struggling to develop receivers capable of operating effectively in the newly contested spectrum. A captured technical document, dated September 1943, and originating from the German Naval High Command, contained a detailed analysis of radar echoes from what were identified as Allied anti-submarine aircraft. The document noted an unusual precision in target acquisition and tracking, particularly at extended ranges. It could not be explained by conventional cavity magnetrons operating at longer wavelengths. The report speculated on the existence of a new, highly efficient microwave generator, though it dismissed the possibility of a practical, deployable device. Further analysis of wreckage from a downed RAF Lancaster bomber in December 1943 yielded fragments of a device later identified as a 10-centimeter cavity magnetron. The components, though damaged, exhibited an advanced design for high power output and frequency stability. The intricate copper anode block and robust cathode assembly confirmed the Allied mastery of microwave generation, a technological leap that had been deemed unattainable by German radar specialists just months prior. The sheer volume of new intelligence, from operational reports to technical specifications, painted an undeniable picture. The Allies were not just experimenting with microwave radar. They were deploying it on a wide scale, integrated into their bomber fleets and naval patrols. This widespread application, particularly in airborne systems, demonstrated a manufacturing capacity and a scientific understanding that profoundly shocked German engineers. The implications for air defense and anti-shipping operations were catastrophic. The sheer efficiency of the cavity magnetron, now confirmed by meticulous reverse engineering, presented an undeniable strategic imbalance. German radar development, while robust in theory and application, had been primarily focused on high-power, low-frequency systems, optimized for long-range detection against conventional aircraft formations. The Allies' adoption of the magnetron, however, signaled a decisive shift towards centimeter-wave radar, offering unprecedented resolution and compact size, fundamentally altering the calculus of air defense and offensive navigation. The captured components, particularly the resonant cavities and the precise cathode structure, indicated a manufacturing capability far exceeding initial assessments of Allied technical prowess in this specific domain. Interrogation reports from downed Allied aircrews correlated with intelligence intercepts began to paint a clearer picture of the widespread deployment of these new radar sets. Production logs from British factories, later acquired through espionage, revealed a staggering output. Over 20,000 magnetrons per month by late 1943, a figure that dwarfed any comparable German high-frequency component production. This industrial capacity, coupled with the inherent advantages of the magnetron, meant that Allied aircraft could operate with greater precision in adverse weather and at night, rendering traditional German flak and night fighter tactics increasingly obsolete. The technological gap was not merely theoretical. It was manifesting in tangible operational losses and a growing sense of vulnerability. The German scientific community, particularly those within the Reich Air Ministry's research departments, understood the immediate and dire implications. A memorandum from Professor Hans Ferdinand Mayer to Field Marshal Erhard Milch, dated November 1943, starkly outlined the necessity for a rapid acceleration of indigenous centimeter-wave radar research. He emphasized that without a comparable German magnetron or an equally effective alternative, the Luftwaffe's ability to defend the Reich would be severely compromised. The memo detailed the specific power outputs and frequency ranges of the captured magnetrons, noting their suitability for airborne intercept and ground-controlled interception roles, areas where German systems were now demonstrably inferior. The response was swift, albeit burdened by existing commitments and material shortages. Research programs previously considered secondary were immediately elevated to top priority. Efforts to replicate the Allied magnetron or to develop a German equivalent consumed significant resources at institutions like the Telefunken Laboratories and the Kaiser Wilhelm Society. Engineering teams meticulously studied the precise copper alloys used in the resonant cavities, the vacuum sealing techniques, and the complex electron trajectories within the devices. The challenge was not just scientific, but also industrial, requiring new manufacturing processes and a specialized workforce. The strategic implications extended beyond immediate air defense. The compact size and high resolution of magnetron-based radar systems also offered significant advantages for naval applications, particularly in submarine detection and anti-shipping operations. Damage reports from U-boat command indicated an increasing frequency of Allied air attacks, often in conditions of poor visibility, suggesting the deployment of sophisticated airborne radar. The captured magnetron provided a stark explanation for these previously inexplicable losses, confirming a technological leap that directly threatened Germany's naval strategy. The realization settled in. The war had entered a new phase, one where technological superiority in radar would be a decisive factor. The initial disbelief at the Allied achievement had given way to a grim determination to catch up. Factories across the Reich, already strained by conventional armaments, production, were now tasked with the monumental effort of developing and manufacturing entirely new classes of electronic components. The blueprint for a German cavity magnetron, designated Clandestine C, was finalized in early 1944, calling for 500 units per month by year's end.